Okay, this is a quick video about finding the components of one vector along another vector, which sounds like a weird thing to do, but turns out to be enormously useful down the road. So let's take a look. This is a vector A. A vector is nothing more than an arrow that has a length and points in a direction. So check, that's a vector. Of course, if we want to assign numbers to that vector, we need some sort of coordinate system. So what you do is you set up an X and Y axis, you measure what that angle is, and now what you can say is, look, I know how to add vectors. You just take two vectors and you put the tail of one at the tip of the other. And so I can make the vector A with a vector that points along my x-axis and a vector that points along my y-axis. So that looks like this. We take the sine and cosine because of trigonometry. These pieces are called the projections of this vector onto the x and y axes. So the arrow is the projection on each axis. What we're mainly interested in this video is, what is the size of those arrows? That is called the component along the x direction. And so we can write the vector A as an arrow along the x plus an arrow along the y, and the size of each of those is called the components. We can write it in a more compact way like this, where we just say the vector A is given by its x component and its y component. Done. Now, let's say that instead of wanting to go along the xy axis, we have a second vector, B, and we ask the following strange question. What is the component of A along B? And that seems strange, but if you think about it, I can just make two different arrows like I did exactly the same way when I had axes. In other words, I build the vector A with this arrow, and I build the vector A with this arrow. I add the two together just like I did last time. This is nothing more than rotating my axes. I've rotated my axes up to the vector B so that B is now my x-axis. That means that if I know the angle between A and my new x-axis, I can find the projections exactly the same way as I did last time. This means that if I want to build the vector A, I now use the projection along the B hat direction and the projection along the perpendicular to the B hat direction. And so if you don't like the terms B hat and B perpendicular hat, just think of it as x prime and y prime. But I'll tell you, it's not really any different than what we did before. I could have just as easily written x hat and x perpendicular hat. We just happen to call x perpendicular hat y hat. That's the only difference between what we've done. Meanwhile, I can express it in the same compact notation I did before, but I have to be a little careful here, because if I don't put this guy B here, people are going to think that I mean those are the x and y components. And these are not the x and y components. These are the B and B perpendicular components. So if there's just numbers there, no one knows what the components are. So you have to tell them, okay? All right, let's do a concrete example with numbers. So I have two vectors here. They're both given in Cartesian form. And the first thing I need to do is find the angle between them. So you find the angle between two vectors most easily by taking the dot product between them. And so just recall that that's magnitude of A, magnitude of B times the cosine of the angle between them. And then a dot product is defined as multiplying the components and adding them, okay? So if I punch in all the numbers, I get something that looks like this. It's pretty straightforward to solve for theta. And so if I want to express A in terms of projections along B and B perpendicular, another way to say that is in terms of components, I express it like this. And if I punch in the numbers, I get this. So this idea is super weird, but calculating it is as easy as finding the components along the x-axis. You've just changed what you mean by the x-axis. I want to give you one final thing. If you take a look at what we have here, we have A cosine theta and A sine theta. If you remember your dot and cross product, there's actually a really nifty way to express the components along the axis in terms of dot and cross products. Now, I put a big box around this at the end, like, oh, this is the important thing to remember. I'm not saying remember this formula because it's important. What I'm saying is try to understand this geometry. If you understand this geometry, you'll be in good shape. The reason I put this is to show a nice example of how dot product and cross product play with each other to construct new coordinate axes. Okay, hopefully this video was more helpful than confusing.